Maybe dim on this side at least. Hmm? Yeah. I think it's on.
Okay, greetings everybody. We're going to get started. Thank you for joining us. Thank you for joining us for NOAA AOML's Physical Oceanography Division seminar series. Our speaker today is Dr. Matthieu Le Hénaff, and he got his PhD in 2008 from the University of Paul Sabatier in Toulouse and has been working at AOML as a SEMA scientist since 2015. He's going to be talking to us today about the impact of ocean conditions on hurricane forecasts, specifically looking at the 2017 and 2018 hurricane season. So with that, I'll pass it to Matthieu. But before I do, for those of you listening via GoToMeeting, please remember to mute your speakers. And for those of you in the audience, if you have questions, maybe we'll try to use the microphone so that the folks listening in can hear both the question and the answer.
Thanks, Renelise. Thank you all for being here today. I would like to acknowledge my co-authors for this work, George, Ricardo, Gustavo, Francis from AOML here, and also Hansu Kim and Jili Dong from NOAA EMC at College Park. So today, the outline of my presentation, I'll first go over some motivation for our studies, then I'll talk briefly about the methodological approach, and then I'll present results and discuss them before concluding. So the motivation, we know that there are large densities of population in the Southeast US and the Gulf of Mexico that are regularly impacted by hurricanes, but that's also true for the greater Caribbean and the Antilles with the very densely populated islands, in particular Puerto Rico and other islands in the Lesser Antilles. And in the US alone, since 2005, there's been 1,400 deaths due to hurricanes, and each storm making landfall cost on average $15 billion. And the growing populations on the coast, along the coast, will make the problems more acute probably in the future. And so it's essential to have accurate forecasts to efficiently plan and prepare during the hurricane season. So that's what NHC has been doing. And those are quite famous plots of the improvement of the quality of the forecast in the last 30 years. So on the left is the reduction of the error in the track forecast for the storms in the last 30 years, and each color represents the forecast lead time from 1 day to 5 days. And we see that in the last 30 years, the improvement has been more or less constant, but it's not as pronounced for the wind intensity, which is the plot on the right side, and we see that the improvement is not as good as for the hurricane track. And one area of improvement for the hurricane wind intensity forecast is to better take into account the interactions between the ocean and tropical storms. And that's the importance of the ocean has been demonstrated at multiple times, and this is, for example, in particular, the ocean eddies have been shown to play an important role in the intensification on some hurricanes, and that was the case in particular for Hurricane Opal in 1995 and Katrina in 2005. This is a famous figure for Katrina that shows the tropical cyclone heat potential, which is the heat reservoir that the storm can feed on. And we see that the storm, the intensity of the storm is in the colored circles. The storm intensified when it passed over a loop current eddy that is filled with warm waters. So the vertical structure is key, because if I plotted the sea surface temperature at that time, in the summer, the sea surface temperature in the Gulf is uniformly warm, and that's really much more the vertical structure that matters. So ideally, hurricane forecast models should take into account the correct representation of the ocean features, in addition to representing the interaction between the ocean and the storms. So that's, for the first part, ocean models can assimilate observations to better represent the features in a more realistic way. And second, we want to use coupled ocean atmosphere hurricane models to represent the interactions that take place between the ocean and the atmosphere. And in complement of these modeling considerations, there is also an effort to put in observations, and that's what AOML PHOD has been doing since 2014 with the deployment of dedicated gliders in the Caribbean Sea and the Atlantic region where hurricanes intensify. And the goal is to gather observations to better characterize the interactions between tropical cyclones and the ocean underneath, and also to improve the realism of the models that are used to initialize hurricane forecast models by the assimilation of these glider observations, in addition to standard observations such as satellite altimetry, satellite SST, and in situ Argo profilers. So in this context, AOML PHOD has developed a modeling capacity dedicated to performing observing system experiments and observing system simulated experiments. And the goal is to assess and improve the observing system that is dedicated to hurricane forecasting. And the initial results have been demonstrated in the Gulf of Mexico, and those are the early papers from George Halliwell et al. That introduced the rigorous OSSC methodology to oceanographers. The system has been upgraded recently to the North Atlantic hurricane region with a forecast model with data assimilation at 112-degree resolution. And this configuration has been used to test various observing strategies to improve ocean state estimate for hurricane application. And George presented some of those results yesterday with, for the OSCs in 2017 and 2018. And so the next step is to examine the impacts of ocean observations, which were first tested in the ocean-only model, but this time on hurricane forecasts themselves. And to do that, we use the coupled HICOM HWAF model that uses the same ocean model as the one that has been used to test the various observation networks with the ocean model only. So the coupled HICOM HWAF model that we've been using is adapted from NOAA EMC configuration developed by Hanso Kim at EMC. It's the H218 version with 3 domains with increasing resolution, and the 2 interior nests move together with the storm. It has 75 hybrid pressure signal levels on the vertical. And we use this HWAF version and we replace the HICOM component of that was used in EMC by our in-house HICOM model of the Atlantic hurricane region. And this model again has 112-degree resolution, 26 vertical levels. It's the same model that has been used to test the impact of various observations in the ocean. And so that we can examine the impact of different varying initial conditions at the beginning of the coupled simulations while keeping the same atmospheric component, so that we can really isolate the impact of the ocean. And today I'm going to present results on the 2017 and 18 hurricane seasons, and I'm going to present some results from forecast simulations, which we call forecast cycles. So there are 5-day forecast simulations using this coupled model. So first I would like to talk about the 2017 hurricane season. So in the Caribbean Sea and Atlantic warm pool area, 2017 is marked with very warm waters. We see very high SST of 28 to 30 Celsius, and they are associated with a very large tropical cyclone hit potential, especially in the Caribbean Sea. And in addition to these warm waters, we see here the sea surface salinity derived from satellite observations. We see the signature of the Amazon and Orinoco rivers, and we know that low salinity waters at the surface tend to form barrier layers in which the stratification on the upper part of the ocean is dominated by salinity rather than temperature, which is usually the case. And such barrier layers tend to favor hurricane intensification because they tend to suppress the upper ocean cooling that is due to the tropical cyclone. And here is a map In purple is the area where the surface waters are both warm and with low salinity. And we see that 3 major hurricanes from the 2017 season intensified when they passed over that region. And if we zoom in, we see here the area where the AOML PHOD gliders were deployed, north and south of Puerto Rico, and those gliders were able to sample through these type of water masses. And what they found during the passage of the 3 storms, this is a vertical profile of temperature on the left, salinity on the right, during the passage of Irma. In red is the profiles before the storm, and blue is right after the storm. And the green profiles is from the climatology for reference. So we see that during the passage of Irma, the surface waters were warmer than climatology and with more fresh water, so more intense signature of the Orinoco and Amazon River. There is a weak barrier layer, which we can see because the thickness of the surface layer of constant salinity is slightly shallower than the thickness of the layer of constant temperature near the surface. And after the storm, in blue lines, the blue profiles, we see the deepening of the mixed layer during the storm, and that led to mixing and increase of salinity and reduction of sea surface temperature. And just a few days after, Hurricane Jose passed over the wake of Hurricane Irma in the region sampled by the glider, and we see the different signature of the storm. This time there is little modification in the surface layer, but roughly a deepening of the mixed layer. Now, if we go to Maria was sampled by 2 gliders south of Puerto Rico. And we see in the first one, there is a very thick barrier layer. The surface layer of low salinity is very marked and very shallow compared to the layer of constant temperature. And during the passage of the storm, this stratification was greatly eroded by the passage of the storm. But the second glider showed very different conditions. In that one, there is almost no barrier layer and very limited impact of the storm. So we have different signatures depending on where you are in the ocean. So for the 2017 hurricane simulation, we tested 6 configurations for the ocean model to use for initial conditions for the coupled HRF-ICOM model. So we have one case with no data assimilation. It's the unconstrained run. One in which we assimilate all ocean observations. That is our control simulation, and 6 additional simulations in which for each one we add, in addition to the unconstrained simulation, only one type of observations, namely Argo profilers, glider, SST, and satellite altimetry. So a quick word on glider. So for those who were not here yesterday during George's talk, so on the left is the TCHP from the unconstrained simulation. At the top, at the middle, the simulation with glider data only assimilated, and the difference between both at the bottom. And on the right is the same for the SST. And we see that the signature of assimilating gliders is very marked in tropical cyclone heat potential. And when we look at the difference between the unconstrained simulation and the simulation that assimilates those observations, we see that the signature tend to extend downstream of the location of the gliders with respect to the dominant current system. Now, the situation at the larger scale for the basin in 2017, that's the average during the hurricane season. On the top left is the observation of tropical cyclone heat potential, and there are 5 simulations to the right and the lower panels. So we see that the unconstrained model has a very low TCHP compared to the observations, and the simulations that assimilate Argo profiles and SST are the ones that get the closest to observations as far as TCHP is concerned. I just showed the limited impact of gliders, and then for altimetry, we see that altimetry does not improve the representation of TCHP. Yes, Sim?
I just wasn't clear yesterday. How often are you doing the assimilation?
Every day, once a day.
So once a day?
Yeah.
And this is an average from August 21st to October 7th?
Yes.
So in answer to Gustavo's question, it's not surprising that you have global impact because you're running the model for a few months.
You trigger a divergence by slightly perturbing the model in a repeated manner. Yeah.
One started January 1st.
Right.
Also.
But if you're adding observations, in a couple of days, you're going to have a global impact.
In a few days, it's like straight around.
Yeah, you're kind of shaking the system, even if only locally. Yeah, I agree. And so we first performed some simulations for Hurricane Irma. So I'm going to present briefly results for two cases, the control case and the no-DA case. And for those cases, this is the pre-storm conditions. And as for the seasonal average, we see the control has warmer waters in SST that manifests also in tropical cyclone hit potential due to data assimilation. However, so this is on the one cycle. I'm showing one example of a forecast simulation. On the right, on the left, is the trajectory of the simulated hurricane together with the observed track in blue, and on the right is the intensity forecast. So we see that the coupled model, so this is in red for the no-DA case and black for the control run. The model is able to partially capture the early part of the intensification up to category 5, but it cannot keep the intensity to such a high level and cannot reach as intense storm. And moreover, we don't see a very clear, very pronounced effect, the difference between the two simulations. So the ocean conditions do not appear to have a pronounced effect on the coupled simulations, at least the ones we performed during that stage of the storm between September 4 to 7, when the storm really intensified. So it's not really possible to evaluate the effect of ocean observations for Irma. And we also looked at Jose. I'm going to present also results from two simulations, the control and the no-DA case. And similar to Irma, we have a warmer ocean in the control simulation with warmer TCHP. And this is again the storm track and intensity for one forecast cycle. And we see, as for Irma, a good initialization, but the model is not able to go as to show winds as high as observed. And we have early in the simulation very limited differences between the two simulations, even though around day 3 we start seeing some differences in the sense that the simulation that has initial conditions with assimilation of observations maintain a higher intensity than the unconstrained simulation. But again, the differences are rather limited, and so yeah, we're still working on those storms. Maybe it's possible that later on, when the storm goes over the north of Puerto Rico, where there's the glider data, for example, we see a different signature. And now I'm going to spend more time on the Maria case. So this is the initial conditions for Maria. On top, we see the unconstrained simulation on the left and the observed TCHP on the right, and below is differences between different cases and the forecast model. So the differences between the observations and the unconstrained simulation shows that the unconstrained simulation lacks TCHP, and the simulation that assimilate all observations are control, and the one that assimilate Argo profiles are the ones that go the closest to the observed TCHP. We see again the very limited limited spatial impact of glider observations, and the fact that altimetry alone is not able to fix TCHP. So that was presented also yesterday by George. This is an example of a forecast cycle. We see on the left the trajectories of the storm in the models that are a little too north compared to the observed one. And if we look at on the right, we see the wind intensity for the two simulations in blue. This time, no DA case is in blue, and the control run with all observations assimilated is in red, and the observed value are in gray. So we see that the two simulations are able to represent a very steep storm intensification. Even though they don't reach category 5 as observed, they were able to go to a good category 4, and the OLOPS case is the one that is able to better reproduce such rapid intensification, and clearly it maintains a higher wind intensity later in the storm compared to the coupled model initiated with initial conditions from the unconstrained model. So yeah, this good performance had us look at more. First I want to compare also with the coupled H12 HICOM. We can look at the signature in the ocean during the passage of the storm, which we cannot do very well with the ocean-only simulation. So those are on the left vertical profiles of temperature and salinity, and in red is the profile just before the passage of the storm from the simulation, and in black the profiles from observations. And we see, and then on the column on the right is the Hofmüller diagram on the vertical with time on the x-axis that shows the signature of the passage of the storm that starts 24 hours prior to the storm and goes to 48 hours after the passage of the storm. So we see that for both the simulations initiated with the unconstrained and the NODA and the altimetry only simulations, the ocean is way too cold and not realistic. When assimilating the Argo float, we are able to reduce this cold bias in the model, and the simulations that add glider observations and that assimilate all observations also are the two simulations that really allow to get the lowest temperature difference between the model and observations. And we performed 6 forecast cycles initiated every 12 hours during September 17 to 19, and we calculated the root mean square error based on these 6 cycles, depending on the forecast time. So that's this plot on the right. It's a little complex. So each color represents one simulation with different initial conditions, and the dashed black line is the root mean square error from the NHC official product as a reference. Not that we are pretending we're doing better, but to show that our error levels are realistic, are the ones that are the same range as the official products. So I'm going to guide you through it. So in dark blue is the NODA case, and it's the one that has the largest errors on average in wind intensity over the 3 days. The all-ups case in red is the one that constantly has the lowest error, and which means that assimilating ocean observations lead, in this case, to 20% error reduction in wind intensity forecast, which is not negligible. And all the platforms, on average, contribute to error reduction with the addition of SST and Argo leading to the same level of error at 28.7.8 knots, and at glider and at altimetry slightly larger at 22.5 and 22.4. Now, if we look at the root mean square error, this time not in terms of forecast hours, but in each date during the period between September 17 and September 20. September 20 is the date in which the Maria made landfall on Puerto Rico. Then we see, if we focus on the 24 hours that are preceding the landfall, we see that the NODA case again is the one with the largest errors, over 30 knots. The all-ups case is the one again with the lowest errors, and this time it's a 30% error reduction between the two simulations. And of this total error reduction, the gliders are the one that contribute the most, and the error reduction thanks to the glider is 44% of this total error reduction. And that's because it's the period when the storm was the closest to Puerto Rico, and because the gliders were in close proximity of the island, that's where they are efficient. And that really advocates for the fact that we need a dense array of profilers in order to lead to efficient results. And then we looked at the 2018 hurricane season, and especially Hurricane Michael. So Michael is the first Category 5 hurricane to hit continental US since Andrew in 1992. He also experienced a very rapid intensification from a tropical storm to Category 5 hurricane in about 3 days. That was pretty violent. And in that course, the hurricane encountered several ocean features. So on the top left is sea surface height from altimetry. Top right is satellite sea surface temperature. Bottom left is tropical cyclone heat potential derived from satellite observations. And bottom right, salinity derived from satellite. So we see that the storm came in proximity of a loop current eddy that just detached, and that's again a reservoir of warm waters associated with high TCHP. It also went close to a smaller anticyclonic eddy that detached earlier from the loop current system and is also associated with warmer waters. And in addition to that, it went over the Mississippi River plume, which is prone to form barrier layers, which I described earlier, so that are also favorable for hurricane intensification. And in addition, to these patterns, the waters in the northeastern Gulf of Mexico at the end of the summer 2018 were much warmer than usual. This is the anomaly for September, and that's really the northeast corner where the storm really ranked up to category 5, correspond to much warmer waters compared to climatology. So for this storm, we looked at 5 study cases for the coupled model with the initial condition from the unconstrained simulation, the all-ops control observations, and then we looked at the impact of adding Argo data, SST observations, and altimetry. So here's an example of one cycle very early in the storm lifetime. So again, trajectories are on the right and wind intensity are on the left. So what we see is the tracks generally are close to the observed one, but there is a spread in the early stage of the storm when it was forming, and that manifests also in the part of the coast where the storm made landfall. And the case in which we assimilate all observations is the closest to the observed track. In terms of intensity, the control case with all observations is able to reach category 4 and has a correct date for impact for landfall. And that's the case that performs the best. And the unconstrained case in dark blue does not intensify as much, which is expected. And also, surprisingly, the case in which we assimilated only altimetry does not, the storm does not intensify at all in that simulation, which is noticeable. And from those simulations, we looked at 3 forecast cycles, all started on October 6th, so very early on in the storm lifetime. And this is the root mean square error, similar to what I presented earlier. So what we see from that is the no DA case has large error on the same order of magnitude as for Maria that I presented earlier. The all-ops case has the lowest errors of 12 knots in the 5-day period. So clearly assimilating ocean observations has an impact here, about 45% error reduction. And the assimilation in which we had altimetry alone is the one that has the largest errors. And in between the assimilating Argo profiles and SST observations also lead to error reduction with respect to the unconstrained simulation and show the significant contributions of these platforms. Now, if we look at the wind intensity of each simulation when they reach 29 degree north, which is north of the Gulf of Mexico, close to landfall, actually. So the observed values are 125 knots, and the unconstrained simulation goes only to 80 knots wind intensity, and the all-ops case go to 115 knots. So there is about 77% error reduction when assimilating all observation when it comes to estimating the winds close to landfall. So that's very large error reduction. And also each platform, the platform, the Argo floats and SST observation all contribute to error reduction significantly, 45% and 60% respectively. But one question is, why does the assimilation of altimetry alone degrade the forecast in this case? And so I looked at the initial conditions for 3 simulations: the unconstrained simulation, the control simulation in which we assimilate all observations, and the simulation in which we assimilate only altimetry. So that's the sea surface height, and we see that both the control and the altimetry only simulations show a close sea surface height signature, which is expected from assimilation of altimetry, and they are both realistic. In terms of SST, however, the altimetry only simulation is closer to the unconstrained simulation because SST is not corrected, so that is also expected, and it's much weaker than the actual temperatures that are reflected in the control simulation. And finally, the tropical cyclone heat potential, we see that the assimilation of altimetry at the bottom right leads to forcing a retracted and pretty weak loop current. And just north of it is a cyclonic frontal eddy of the loop current, and the correction of the vertical structure from altimetry leads to a damping of the tropical cyclone heat potential in that simulation that is even lower than a TCHP in the unconstrained simulation. And that's why this features really annihilates the growth of the storm in the simulations initiated with this altimetry-only simulation. And that's why we have the result with such a weak storm. So to conclude the simulations, first for the 2017 hurricane season, we saw with Maria that the coupled HRF HICOM was able to partially reproduce the rapid intensification of the storm. And for that storm, all ocean observations that were assimilated in the model participated in the reduction of wind intensity forecast errors with respect to the unconstrained simulation. The AOML PHOD gliders were efficient in the 24 hours preceding landfall due to the limited spatial extent of their error reduction, and that suggests that a dense network of profilers is necessary if we want to constrain ocean models and represent vertical structure of the ocean on larger scales. And for Irma and Jose, the coupled model suggests limited impact of ocean observations on the intensity of the hurricanes, at least for the cycles that we examined. And yeah, this work in progress, we need to run additional simulations in other stages of the storm because ocean observations might have an impact in other periods. And the results about the 2017 hurricane season in terms of observations and modeling, which are partially presented today, will be presented in Dominguez et al. Major Atlantic Hurricanes of 2017, Impact of Ocean Conditions and Improved Intensity Forecast, manuscript in preparation and is quite well advanced. And for Hurricane Michael during 2018, we show that the coupled HRF HICOM was able to reproduce the rapid intensification of the storm in the early stages of the storm. And the assimilation of ocean observation led to a very large error reduction in wind intensity forecasts, which again stresses the strong impact of the ocean on that specific storm. And we also found that altimetry alone leads to degraded forecasts, and that really stresses the fact that ocean observations work together to improve the realism of ocean simulations. So altimetry is good at fixing the mesoscale features, but it needs profilers such as Argo floats and gliders to fix the vertical structure, whereas SST will give you the correct temperature and so the heat in the top mixed layer of the ocean. And the results about Hurricane Michael in terms of observations and modeling will be presented in Hurricane Michael, the role of the Gulf of Mexico ocean conditions on its intensification, which is also in preparation. And in addition to these 2017 and 2018 cases, more work is necessary to characterize the impacts of specific ocean processes. And I'm thinking the impact of the river plumes from the Amazon and Orinoco rivers in the Caribbean Sea and the Mississippi River in the Gulf of Mexico. What are those impacts on the storm intensity? And also we also want to look at the impact of the eddy field, which is known in the Gulf of Mexico, but we can expect that it also plays a role in the Caribbean Sea. And this is the work to do in the future. And with this, I'll thank you.